Hello, I would like to make another video, this time about the crossout method in the antibody panel, why it works, how it works, the logic behind it, just to reinforce the concepts and maybe clarify any confusion that there may be, because it is, I don't think, that intuitive and it can be a little bit complex, so I just want to kind of put everything together and explain it in one coherent, concise video. So that's what I'm going to try to do right now. So this is an antibody panel from the textbook Figure 10-6. This is the confirmatory panel, not the screening panel. Screening panel has 2 to 3 reagents, and the confirmatory panel has 11 to 20 reagents according to the textbook. And so this portion of the antibody panel is about the reagents and the antigen genotypes of the reagents. And this portion of the panel is about the patient results. So the patient's serum has been tested in 4 different ways, and each column is the result of those tests. IS refers to immediate spin, which means the patient's serum is centrifuged, and this is typically done at room temperature. And as you should know, IgM antibodies are the ones that tend to react at room temperature, as opposed to IgG that typically react at 37 degrees Celsius or higher. And AHG, which chapter 5 is dedicated to, is a reagent that is added to patient serum, and it helps IgG antibodies that didn't create agglutination create agglutination. So it's basically an anti-antibody. So the AHG binds to IgG to allow it to create agglutination, because without it, IgG could bind, but it wouldn't create agglutination because the antibody is too short, or what the book terms as incomplete. So I could show a little diagram here. So this is the red blood cell, this is the antigen, and then this would be the IgG. But it's too short, and so it cannot bind to another red blood cell. So instead, we have the AHG, which binds over here, and then now we can create agglutination. So without the AHG reagent, there would just be a bunch of red blood cells with IgG bound to them, but we wouldn't know that IgG is bound because it doesn't create agglutination. So in turn, we would get a false negative without AHG. That's why in the 37 degrees, we see a bunch of zeros, which are false negatives because, as you can see, IgG is present, but we just need the AHG reagent in order to see that positive reaction. And then CC is Coombs check cells, using Coombs reagent, and so this is used whenever there's a negative result, and a positive check cell. It means that the negative result is actually negative, and I believe chapter 10 goes into what check cells are. And so just a little bit of review. These are the 11 reagent cells, and these you may also hear them called donor cells because these reagents are made from people who donate their red blood cells. And so you may be wondering why I have these arrows drawn here. And this is because some of these antigens in the panel show quote-unquote dosage, and some of them do not. And so I'm going to explain what dosage is and how it affects the crossout method. And chapter 10 explains this a bit in a few paragraphs. but I just want to go into it in a little more detail. So these antigen with arrows do not show dosage, and the ones without arrows do show dosage. And so I'm just going to use big E and little e as an example. So let's say someone is heterozygous for big E, little e. So they'll have plus plus. So this means on the red blood cell, they're going to have both capital E antigen and lowercase e antigen present on the surface of their red blood cells. So this means that they have to share the antigen sites on the red blood cells. And so when there's dosage, that means that maybe there's 100 different capital E antigen per red blood cell, but maybe there's only like 3 lowercase e antigen per red blood cell. And so maybe when the antibodies bind these 3 lowercase e antigens, that it's not enough agglutination to give a positive result. So maybe we get a false 0. That's what dosage means, that the reaction of a heterozygous individual may not be that good of a reaction when testing for antibodies in an antibody panel. And so when we have a homozygous individual, I'm just choosing big E for this example, there's only big E, obviously, right? And so there's no sharing of the antigen sites. It's all just big E. And so in this example, there would be 103 big E. So it would be both of these combined. And so obviously we would get a positive reaction if there were anti-big E exposed to these red blood cells. So there wouldn't be any confusion with this reaction, but there could be with this reaction if we have the 103 situation or something similar. And so this is what the textbook refers to as dosage. And these are the ones without arrows. So what does this mean? This means when we have a negative reaction, that when we have a heterozygous antigen in the reagent, we cannot rule it out, because maybe it's a situation like this, 103. Maybe the patient did have antibodies against the one of these, but it wasn't a reliable reaction. There wasn't enough reaction. Maybe there was something that didn't happen correctly and we get a false negative. So it is standard practice for the ones without arrows for those to be ruled out only if they're homozygous, like this right here. And the textbook explains this in chapter 10, I believe it was. And so the ones with arrows, they show reliable antigen expression no matter whether they're heterozygous or homozygous. So they would have more even expressions. So let's do big K and little k for an example. So if we have an RBC, these would kind of be more evenly expressed. So we have big K, little k, and so maybe it would be something like 50 and 50 is what typically happens. So it's not like the 103 situation. So if we have any antibodies against these, we would more than likely not get a false negative. More than likely we would see any agglutination if there are if there are antibodies against those antigen. And so it is common practice to cross these out if they are heterozygous or homozygous. But I did notice that Anna, our professor, she does not cross these out if they are heterozygous, but you can according to the textbook. And so let's get into the actual crossouts. So I highlighted the rows that are 0 reactions. So no agglutination was observed, meaning all of the antigen in all of these reagents do not have antibodies against them in the patient's serum. So let's see what antigen are present in these reagents as either homozygous or heterozygous and or homozygous. And whatever those antigens are, we can say the patient does not have antibodies against all of them. And so those are our rule outs. And so let's start with row 2. So as we can see, D, as you know, only has one allele, and so it cannot be homozygous or heterozygous. So if it's a plus, we automatically know there's D on the surface of the RBCs, and as we know, there's no antibodies in the patient's serum that recognize them. So we know the antibodies in the patient's serum is not D. And actually, I'm going to cross these out at the top. All right, so moving on to big C, little c. This is homozygous for big C because we have 1 plus and 0. So like we said, since there's no arrow, this has to be homozygous in order for us to cross it out, which it is, so we can cross it out. And then now looking at big E, little e, we have homozygous for little e, so we can cross out little e. And then CW is just like D. There's only one allele for this antigen. So if there's a plus, that means it's expressed on the RBCs. And like we said, we know the patient's antibodies does not have any targets for any antigen on these reagents. So number 2 reagent has CW. Therefore, the patient's serum cannot have anti-CW. And then here is where we get to the ones that we can cross out if it is heterozygous or homozygous. And so essentially we just can't cross it out if they're both 0. So here they're both plus, and so we can cross them out. Here we have KPA, KPB, we have homozygous KPB, so we can cross it out. We cannot cross out KPA because there's 0 KPA. So that means the reagent RBCs do not have KPA. All right, so JSA and JSB, this one is homozygous for JSB, and there's no JSA, so we can cross out JSB. FYA, FYB, this one is homozygous for FYB. There's no arrow, which means if it were heterozygous, we would not be able to cross it out. But since it is homozygous, we can cross it out. And then JKA and JKB, it's homozygous for JKA because we have plus and 0, so we can cross it out. LEA and LEB, there is nothing, we cannot cross it out. P1 is another one where there's only one allele. It's either there or it isn't. Here it is there, so that means the RBCs express P1, but we know that there are no antibodies against any of the antigen, including P1. And then we have M and N, homozygous for M. Oh wait, I realized I actually crossed this out here. I mean, you can do either one, but I just like doing it on the top. Okay, so M and N, we have homozygous for M, so we can cross it out. And here we have homozygous for big S, so we can cross it out. Remember, these ones can only be homozygous for crossouts because there's no arrow. And then we have LUA, LUB. This one is homozygous for LUB. If it were heterozygous, we could still cross them out. And then XGA is another one where there's only one allele. It's either there or it isn't, and here it is there, so we can cross it out. All right, so the professor says we need 3 crossouts, and she does them like this before we can completely rule out an antigen. And it's good because we have 4 rows. That means we have the potential to cross out a lot of antigen 3 times. All right, so let's just repeat the process on row 5. So here there is no D antigen, so we cannot cross it out for reagent 5. And here, big C, little c, they are heterozygous. But remember, since there's no arrow, that means they can only be homozygous for crossouts. So we cannot cross anything out. And then here we have big E, little e. It is homozygous for little e, so we can cross out little e again. CW, it's either there or it isn't, and here it is not there, so we cannot cross it out. And then we have big K, little k. So remember, the arrows means it can be heterozygous or homozygous for the crossout. And here we have homozygous little k, so we can cross out little k again. And then here we have homozygous KPB. We can cross that out. Here we have homozygous JSB. We can cross it out. Here we have no FYA or FYB, so we cannot cross anything out because they're not present on the surface of the red blood cells in this reagent. And then we have JKA and JKB. This one is homozygous for JKB, so we can cross it out. This one, homozygous for LEB, so we can cross it out. If it were heterozygous, we would be able to cross both of them out. P1, like I said, it's either there or it isn't. There's only one allele to express it. And in this reagent, it is present. Since our patient's serum did not react, we know that there are no antibodies against P1 or any of the other antigen. So we can cross it out. M and N. This one is homozygous for M, so we can cross it out. Big S and little s, these are heterozygous, but there's no arrow above them, so we cannot cross them out. Alright, LUA and LUB. This one, homozygous for LUB. If it were heterozygous, we would be able to cross out both of them. And then XGA is not there, so we cannot cross it out. Alright, so I'm going to repeat the process off video, and then I'll come back. Okay, so I have completed the crossouts for the remaining 2 reagents, and basically we can cross out any of the antigen that have 3 or more crossouts. I stopped at 3, so there's just 3. So little e has 3 crossouts, meaning we can ignore little e. There's definitely not little e antibodies in the patient's serum. And then the same with, I think this is little k, yeah. Little k, definitely not a target of the patient's antibodies. KPB, JSB, FYB, JKA, let's see, P1, M, and LUB. Alright, so the next step is to see which of the remaining antigen are likely causing the reactions of the antibodies in the patient's serum. So what I like to do is I like to look at the pattern of pluses and zeros and see if there's one single antigen that has the same pattern. And I like to start with the ones that have no crossouts because those are the ones most likely to be targets, because there's no, remember, crossout means that the antigen was present in the reagent, but there was no reaction in the patient's serum. So if, let's say, that the patient actually had anti-C, the one crossout means that there was one instance in which the patient's antibodies did not react to the antigen that it should have bound to, which shouldn't happen, right? So ideally, the ones without any crossouts would be the one that the patient has antibodies for. And it could be more than one, too, right? It could be 1, 2, 3, 4. But the easiest thing, in my opinion, is to just look for one antigen. Start off with one antigen. Look and see if there's one antigen that explains the reaction. If there is one antigen that explains most of the reaction, but not all of it, that suggests that there may be a second antigen that could explain the rest of it. If that makes sense. That may make sense if you see more examples. But yeah, let's just look starting at capital E because it has no crossouts. So our pattern of patient results is plus 0, plus 0, plus 0, 0, plus. And so let's compare it to E. So already off the bat, this has a 0, and it should be a plus if it were to match with the patient results. So this means that if this means that there was agglutination, but there's no E antigen present. So it's impossible for the antibodies present to be targeting capital E if capital E is not there. So capital E is not the reason that we see agglutination. So already off the bat, we're not looking good. So the second one, it does match. 0, 0, no agglutination, and it's not present. Here, plus, it matches, plus, 0, 0, plus 0, plus. So here again, there's agglutination, but there's no E antigen present. So therefore, E cannot be the one causing the agglutination. So, and here we have 0 plus 0, 0. So this is the opposite situation. So we have capital E antigen present, but there's no agglutination, meaning that there are no, or there's likely no antibodies that bound to the E antigen. But like I said, if it's homozygous, which it is here, heterozygous, sorry. There's 2 pluses, so it's heterozygous, and these are the ones that must display homozygous genotypes in order for us to cross it out. And so maybe this is one of those examples that we talked about, the 103 examples. Maybe there's so few capital E antigen that when the antibodies bound to it, that there was so little agglutination, we didn't see it, and we counted it as a 0, so that would be a false negative. Maybe that's one of the cases, we don't know, right? So that's why we look at all of the reagent reactions. And so the last two, 0, 0, these both do not match up with the patient results, right? Because there's agglutination, but there's absolutely no capital E present. And so overall, capital E is not looking like it is the target antigen of these antibodies. And so let's look at the others. KPA has no crossouts. Maybe this might be the one. And so let's compare the results just like we did. So here we have 0, 0. Well, actually, these are 0 for the whole way down. So if the patient actually did have antibodies against this antigen, there's no way of us to know because there's no KPA present in any of the reagents. And so if none of these other antigen explained the reaction, we would have to do further testing like the textbook stated in chapter 10. We would have to maybe pull out a different lot number because different lot numbers have different reagents, and we would have to find a lot number that has at least 3 kPa, because the book explained rule of 3. You want at least 3 where they're homozygous, 3 where they're heterozygous, and 3 where there's nothing present. Alright, so we have plus and 0. So right off the bat, this matches the patient results, plus and 0. So in this reagent, reagent 1, FYA is present on the surface of the red blood cells, and here there's agglutination, meaning that the patient's antibodies recognize something in the reagent cells. Here, there is no FYA, and when there's no FYA present, there's no agglutination. So here we have plus, and we also have plus and plus. So whenever FYA so far is present, we have agglutination in the patient sample. So here we have 0 plus plus, 0 plus plus. So far this is looking really good, right? When there's no agglutination, there's no FYA. When there's FYA, there's agglutination. And so 0, 0 plus plus, 0, 0 plus plus. So FYA matches the patient results perfectly, which implies that FYA is the only antigen that the patient has antibodies against. But let's just look at LUA just in case, right? Maybe both of these are present and both of these are targets for the patient's antibodies, right? So looking at LUA, this one again, there's not any LUA present in the sample, or in the reagents, sorry. So we cannot rule out LUA because we don't know what the reaction is against LUA because there's nothing in any of the reagents. So like before, further testing would need to be done in order to determine if there are antibodies against LUA. But so far, it looks like FYA is the target of the patient's antibodies. The reactions match up perfectly. And there's not one single cross out, which means there's not one single false positive or false negative. And so that would be the answer for this this antibody panel. And this was the answer in the textbook, so I know it is correct. So thank you for watching, and I hope this helped.